Today we are looking on GraphCodeBERT, so pre-training code representation of data flow graph. So to note that, first we have to, discuss on why a normal mass language modeling objective is not sufficient for source code. Why do we not say, why do we need, something more than that? So first thing is that source code is more structured compared to natural language. Next one, the second point is that, representing or learning the representation of source code as series of text token is not viable because there is a lot of underlying structure inside code, which we might not be able to capture in just series of tokens. We are looking code as series of tokens. The third and most important reason is majority of source code based learning tasks required, some implicit capturing of code semantics. So what do I mean by that? So for instance, you have code similarity direction, right? So you have two blocks of code, which if you'll see as series of text, it won't be necessary, or even the syntax would be deviant. We'll have to check the semantics of the code to unifiedly represent two ways of writing code in a way to do that. So generally, basic primer is that what are the various representation of code. I hope that this is readable. So one, we can represent them as raw text tokens, which is the human readable version we all see. Where that is how Elixir sees a code. So Elixir is nothing but a component in your compiler which sees series of character tokens and start assigning lexical tokens to it. We can use abstract syntax tree, which is a tree data structure, so which captures the structure of a given code. And then we can use data flow graph, which which captures the data interaction or transfer between variables and hard-coded values in a given code. And then there's control flow graph, wherein wherein it's a graph wherein each node is a statement, and then you kind of draw the control flow of the program over there, and then executional flow graph is there, which is executed version of control flow graph, wherein you capture the exact transfer of control from each statement. So let's say if there is a conditional statement like if a is greater than 5, so is it going to the then part or the else part is one thing, where executional flow graph captures that detail, right? So seeing to that, executional flow graph is dynamic representation, because to have an executional flow graph, you will have to run the code and you will have to do live variable analysis to make those decisions, because to get there. I mean, just a primer. So okay, so what is semantics in context of code? So we have all of us, to some extent know semantics of linguistics in natural language, but what is it in code? So if you'll ask me, I'll say syntax is how. So how something is written is syntax. What is written is semantics. So given a piece of code, what is semantics? If you'll ask me, I'll say, it is a property of code which answers, what a given piece of code does. So again, reiterating, majority of source code based learning tasks require implicit capturing of the code semantics. So right now, before going there, so one of the ways, right, earlier we discussed about various representations of code. So one of the ways we can capture semantics is through a data flow graph. So data flow graph, is a graph wherein each node of the graph is either a variable token, identifier token, or a hard-coded value, or an operator or an operand. So operands are variables and identifiers, right? So this is how a data flow graph looks for a code like this, which pretty much captures the entire data flow of the structure of how data is flowing from the initialization and what happens in computing these variables. So this is the semantics we are looking for, and the reason for this paper to select data flow graph is because ASTs might differ when it comes to different languages, but data flow graph is kind of constant. So I've written the same piece of code in Python and JavaScript. If we have the data flow graph, it's going to look strikingly similar, because data flow is devoid of code syntax. To compute data flow, we are sure going to need ASTs, but data flow graph is kind of universal. It's ASTs might differ, but data flow graph is kind of universal. But still, there are a class of ASTs called as universal ASTs, which give one unified representation irrespective of what programming language you give it. But then data flow graphs are universal. So just a primer on DFG, because this paper is called as pre-training with data flow graphs, pre-training code with data flow graphs. So given a source code, first thing what happens in computing a DFG is a standard procedure. So first we'll parse it to an AST, first thing. And then second, we have lexical analyzer, and then we start identifying all the variable tokens, right? So like they've done over here, wherein it is the catch is that a graph, each node is a unique one, right? So we can't have one representation for the node A, the variable A, right? Because here we are trying to capture the dynamics involved in data flow graphs. So what we generally do is that we kind of number it down so that variable relation is captured in this way. So the same variable A is numbered in different occurrences as different nodes, right? So that you can actually capture what is happening with them. So right now, unlike this version of data flow graph wherein we had operators too, these people, the authors, use a minimalized version of data flow graph wherein they are only caring about where the value comes from. So we call it as used def edges, so used and defined edges. But they are not caring about what kind of operation is done to the value, or what kind of condition is being called, unlike a standard data flow graph, which will look something like this. So what is prelude to this paper? The prelude to this paper by same set of authors, I hope a major set of authors, is CodeBERT. So CodeBERT was one of the first, if I'm not wrong, first transformer-based pre-training paper for code. So what they did was, instead of just they did Electra kind of thing, wherein you'll have a generator and a discriminator, and we find out the replaced tokens versus the original tokens. But the catch over here is that we don't just model code; we bimodel code with natural language prompts. So because a lot of natural language semantics is equivalent to code semantics. So natural language is an important element, right? Because in identifiers, hard-coded values, developers tend to incubate natural language context to it. So what they did was, using one of the datasets called as CodeSearchNet, they started making bimodal versions of code and comments together. So this particular entire paradigm of software engineering is called as naturalness in code. So it's a pretty interesting field of area wherein they try to bimodal code and comments and look on what implications both have and on each other, right? So any codex related or any of the latest program synthesis or anything we see with respect to codexes comes under naturalness in code. So this is what they did initially. So what is GraphCodeBERT, right? So we'll just look onto it. So GraphCodeBERT, models natural language prompt alongside code chunk, alongside variable sequences together. So like I told, the objective for the model is three different things. One, it has to do the regular masked language modeling objective. So wherein at random these tokens are masked. So let's say return maximum value is the comment, right? Comment over here. So we mask maximum and ask the model to predict what it is. We do that for code and text combinedly in a random fashion, like we do back then. But the catch is that we also give these variable sequences. So this is coherent with I guess it's here. So this is coherent with each node of the data flow graph. So we see that A1, B1, X3, 0, 4, so and so over here, and then we have the same thing. So right now, the second objective for the model is to predict data flow edges. So over here, so we have 11th token, which is X, right? And then 9th token. So if you see the data flow graph over here, there is an edge between token 9 and token 11, right? So over here, the task is to predict if at all two variables are, connected with the data used fh in the data flow graph. We want our model to learn to pick up this connection. So that is what is happening over here. So the second objective is to, I guess I've written, yeah. First one is normal mass language modeling, unmasking and mass tokens. Second one is we have data flow graph edges. From variable sequences, we want to, predict these edges out. This is the second thing. The third thing is that variable alignment across source code and data flow. So what happens over here is that we have variable sequences, we have variable tokens over here, and then we want to check if they both are same with respect to the source code. So this is the most important part. This is the part wherein we bimodal data flow graph structure alongside source code. So over here we have token x, right? So token x is 3. What is 3 over here is this x, right? So the assignment statement of x equals 0 over here. So we are aligning this data flow graph, this particular node in the subgraph, with the actual source code. So what happens while we do this for almost all the samples in the data set? We kind of start establishing this connection between the raw textual source code and the data flow edges. So these are the three objectives alongside bimodeling, where first one is to mask, unmask text and code together in a random fashion. Second thing is that to make the model learn this implicit structure of data flow graph. Third one is to make our model, bimodal source code alongside variable sequences. So it's like aligning, so they call this a variable alignment, wherein nodes in this data flow graph is the model is learned to associate nodes in this data flow graph with source code, raw source code tokens, right? So this is the second thing. So how do they do that? So they have a pretty, how do they mask this? For masking, they have a simple formula. So while having, so if at all the given query is CLS or special tokens, right? They assign 0 to it, or if it belongs to both. I guess this is comment and this is source code text. So if it belongs to both source code text and comment, they'll give it 0. And then if it belongs to data flow edges, so they'll give it to 0. Otherwise, everything is negative infinity. The normal minus 100 thing we do. It's just they've given negative infinity over here. So this is how the masking thing looks. And yeah, so this is the thing. But the catch over here is that they are not, choosing one language and one particular language and doing this. Their data set has plateau of languages. They pre-train them together. The reason why they are able to do that is because the data flow graph is almost the same universally across all languages, irrespective of the language's syntax. Data flow graph is always going to be same. So they've done certain benchmarking with the regular code related tasks. First one is semantic code search, wherein you have a set of data points, code data points in your space, and then you want to, given a natural language query, you want to pick up one particular data point. So they've come with benchmarked against different models like normal Robert on which was trained on natural language, pre-trained on natural language text, and fine-tuned over here. Robert code, so a specific code Robert CodeBERT, their initial works wherein they might bimodel the code and text but not the data flow graph, and then GraphCodeBERT. It seems that GraphCodeBERT performs well, for which the reason being again, almost any code related task, right? So which I wouldn't say almost any, instead I can say every amount of tasks we are going to see are implicitly rely on semantics of code. So since they pre-trained pretty much to capture the semantics of code, I guess it performs well in almost everything. So this is the most important part, wherein semantics of code is directly applied. So over here you'll have two pieces of code. You'll need to classify if these pieces are code clones semantically or they are not, right? So over here your AST, your syntax might deviate a lot in these two samples, but then semantics, as I said, underlying to it is going to be the same. So again, GraphCodeBERT, seems to perform well, but by a slight margin, because almost other models are equally potent enough to handle this task. Code translation too, again, this is before this apps and codex era wherein the standard way of doing is to have a ground truth and have a blur score computed with it, so to check how far the translation is good. So again, they seem to use the have better outputs over here. The other task is code refinement, which is bug fixing. So you have a bugged code, and then you'll have to fix the code to a bug-free version of it using your model. So I guess the encoder is this, and they used a standard transformer decoder to do this. So again, GraphCodeBERT performs well to it. But this task is pretty difficult. So you could see that exact match accuracy is very less compared to code translation. So now they also did pretty good ablation study to check if what aspect of GraphCodeBERT actually helped in solving this entire thing. So you could see that so they had the standard version which with all three objectives. First thing, without edge prediction objective. Next, without node alignment between data flow graph and source code text, raw text source code. And then the third one was without the data flow graph itself, the entire part of data flow graph. So they found out that without data flow graph, it is terribly going wrong. So they have found out that it's an important aspect to capture all these things, because if you'll wrap your mind around it, so it's like explicitly train your model to capture something which is going to be very useful. So we had we initially in the first slide we were discussing that AST is also another form, right? So what happens if we use ASTs instead of TFGs? So they found out that it pretty much kills the performance, even in certain sequence lengths. Without any code structure, just raw text tokens were able to perform well. But GraphCodeBERT uniformly performed well in the score with mean reciprocal rank score, because again they argue that data flow is less complex, right, which makes sense. And also, since each node is just an identifier or an operator, right? The number of nodes in the graph or the size of the graph is very less, so you could accommodate between 512 your sequence length. But when it comes to ASTs, it's pretty much complex because you capture the entire hierarchy. You start from your code block, statement list, statements, and then you come to the identifier. So the entire hierarchy involves, the tree is pretty much larger compared to that. So again, this is one thing. So finally, to conclude the thing, they were talking about error analysis. So where did GraphCodeBERT go wrong? First thing is understanding API code structure, which is one of the problems, or which is one of the most difficult things with modern programming languages. So you have to show each API has its own syntactic structure, but it is a blessing for people who are working with legacy codes, because you don't have API calls over here. So when we has return an image tensor, right? So it was terribly, the ground truth was something like this, but it was terribly cribbing to, give out something else, which is pretty understandable because it wouldn't have seen enough amount of, code to learn a particular API code structure. So they specifically talked about TensorFlow code and then having Google Cloud API code, so which had some problems with it. Oh, interestingly, it used S3 buckets for Google Cloud. I mean, okay, it's just a funny thing. And the second thing is that this happened with GPT-3 versions, but Codex has improved this. Semantic errors. So, an uninitialized variable being used somewhere, such errors started coming up, one thing over here. And as usual, irrespective of these models being very big, right? It generating the right syntax is pretty difficult. I mean, even for I'm talking before Codex. Codex, oh no, I'm talking about Copilot, right? So Copilot engineered version is pretty good at this, so it doesn't make these errors. But I guess a lot of GPT-3 fine-tuned versions have this problem. So syntactic errors are still part of that. Yeah, I guess that's it. I mean, with respect to this, so key takeaways is that when they started, incubating these implicit structures of code over here, which will be useful for the a lot of tasks. They found out that these models a surge in performance first thing.